Okay. If acceleration is uniform, then the average velocity occurs at the midpoint in time. So, here's a typical velocity versus time. And the average velocity occurs halfway between the initial and final time in that interval. So for example, if you're timing something rolling down a ramp, or if you're timing a rotating beam or whatever, a rotating object, if the acceleration is uniform, this is going to be the case. Now, if it's not uniform, it's unlikely to be the case. If it was curved, it would have to curve just right if the graph is curved. Of course, what I mean by uniform acceleration is the rate of change of velocity is always the same, which means the slope of the graph is always the same. Now, that's one thing you have to understand intuitively, why a straight line velocity graph means uniform acceleration, and uniform acceleration means that the graph of velocity versus time has to be straight. So you want to ponder that. Acceleration, as we've said, is the rate of change of velocity with respect to time. Change in velocity divided by change in time. So that's an average acceleration. If acceleration is uniform, then it's always equal to its average. And you want to ponder that. You want that to be intuitive. I talked about how, excuse me, my nose is itching from wearing the mask. You understand intuitively why it is that if I tell you you're making $10 an hour and you work for 6 hours, you can tell me instantly that you're going to make $60. Okay. If you know your pay rate and how long you work, you know instantly to multiply those. You don't have to go look up a formula. You don't have to think of a formula. You know it in your gut. Okay. If you work 12 hours and make $180, well, you might not be able to do the arithmetic instantly in your mind and tell me it's $15 an hour, but you know that you're going to divide how much you make by how long it was. Those are rates of, that's a rate of change thing. Your pay rate is a rate of change. Okay, it's a change in how much money you've made with respect to time. Okay, divided by a change in time, which is an average rate of pay with respect to time. Okay. Now, in the situations we're looking at, we often start with velocity 0. So this is what your graph would look like. Your average velocity occurs at the halfway time. I've written here initial velocity is 0 and v0 is 0, and it occurs at time t equals 0, and we call that time t0. It's not exactly a rigorously written statement there, but we understand what it means. Okay? The other thing we know, of course, is the final velocity is a velocity at the final time. And if this is a straight line, which it is because acceleration is uniform, provided acceleration really is uniform, then this triangle here is geometrically similar to this triangle here, and this triangle has half the base, if this is the base, of this triangle, which means that this altitude is half of this altitude, so the average velocity is half of the final velocity. Now, some people have a little trouble with the idea that the average velocity is half the final velocity. So you want to ponder that. And I said, well, think of it. This thing's rolling down the incline. It starts at 0 and finally reaches its final velocity. Now, if I have another one on a level so it doesn't speed up or slow down, and start it at that final velocity, it's going to immediately be ahead of this one, and it's going to stay that way because this one doesn't reach the velocity of this one until it gets to the very end. So this one's always going to be moving faster than this one. The one with this, the final velocity being, the velocity always being equal to the final velocity, will always be moving faster than this one until that last instant. Okay. So you want to think about that to make sure you get that. And my point is, all this needs to be as intuitive as pay rate, time, and how much you earn. Okay? And this is a feasible task. If you make this intuitive, then you understand things a lot better. Okay, so anyhow, so we've established, first of all, that because of the straight line graph, whether you start from a non-zero velocity or not, the average velocity occurs at the midpoint time. In the case where the initial velocity is zero, the velocity at t equals 0 is 0, then the final velocity has to be double the average velocity because of those similar triangles. And that's not the case here. You know, the final velocity is up here, and this final velocity is clearly not double the average velocity. So you can't use this idea that the final velocity is double the average velocity unless initial velocity is 0 and acceleration is uniform. Now, there are actually non-uniform accelerations. You could contrive where that might be true, but it's not something you can rely on, and it would very rarely be true. Okay? So, again, what we're doing here, what we're going to do is confine to this case. It does not work in this case. You really want to understand that, because people get in the habit of calculating an acceleration by this quick method that we're going to show. It applies to what you've done in lab today. And then apply it when the initial velocity isn't 0, or when the acceleration isn't uniform. And that's a fatal error, okay? Okay, so for this particular situation, the graph looks like this, or maybe goes through the origin like this. Notice the graph is through the origin, and time starts at 0, goes to some final time. This is going to work. Okay? So, in this case, you have this. Now, you also have, well, then the acceleration is change in velocity divided by change in time. Change in velocity is the final minus the initial velocity. Change in time is the final time minus the initial time. If the initial velocity and initial time are 0, then this just becomes final velocity over the final time. Okay, notice change in velocity is the final velocity, change in time is the final time. Now, as I say, also obviously, it should be obvious, but apparently isn't quite obvious. So again, you want to make it obvious. An average rate of change of one quantity with respect to the other is the change in this quantity divided by the change in that quantity. Change in the first by divided by the change in the second. Change in the dependent variable divided by the change in the independent variable. That's what an average rate of change always is. An average velocity is an average rate of change. Remember, this is a pre-calculus concept, and then it's developed in calculus, and it's taken to the limit as the time interval goes to 0, so it becomes instantaneous velocity, which is a derivative of your velocity function. So that's important. If you haven't gotten that far in calculus, you will, and then you'll understand the calculus better. There are advantages to learning calculus at the same time you learn physics, which is why I learned it, because they reinforce each other so beautifully. You constantly have physics examples of what you're learning in calculus. And you understand the physics better because you know the calculus, and you put them all together, and you just learn both things better. There are also disadvantages. There are advantages to knowing calculus before you take physics. And you know, some schools do it that way, some schools do it concurrently. They're both right for a lot of reasons, and they both lose the advantages of the alternative for the similar reasons. I think it's kind of a wash, but I kind of like concurrent, because that's the way I did it. Okay, so bottom line, you take how far the thing went from rest and divide it by the time interval, and if what that is your average velocity, and then you take the average velocity, double it to get the final velocity, again, which you can only do under this condition. The graph looks like this. and you get the acceleration. So it's a very simple calculation. So if something travels 180 centimeters in 10 seconds from rest, then you know its average velocity is 180 centimeters divided by 10 seconds, change in position divided by change in time, rate of change of position, 18 centimeters per second. If, again, acceleration is uniform and initial velocity is 0, then your final velocity had to be 36 centimeters per second. And your acceleration is your change in velocity, well, from 0 to 36 centimeters per second, divided by the 10 seconds, you get 3.6 centimeters per second squared. There's your average, that's your average acceleration. If acceleration is uniform, that is your acceleration. Now, for the experiment where you saw how far the thing goes after leaving the edge of the ramp, we know how high that was, it's about 1 meter. You can easily determine what the final velocity actually was and see if the acceleration you get from that, or the final velocity you get there, matches the final velocity you got here. Okay? If not, then the acceleration wasn't uniform. Now, they're not going to come out exactly the same because you're using data that can't be measured exactly, things that can't be measured exactly, okay? But if they're reasonably consistent within experimental error, then you're confirming within that experimental error that the acceleration really was uniform, as it should be theoretically on a uniform incline, a smooth uniform incline. Okay, so that's kind of what we're after here. Now, I've also said some things about how you have to have the experiment written up ultimately. You want the experiment to be written up in such a way that I could send it to any knowledgeable physics student, any physics student who knows, say, who's had a good physics course. And they would be able, if they had the apparatus that you have, or equivalent apparatus, to verify your conclusions. So experiments need to be verified. That's the way science works. You do an experiment, you report it, people try to verify it. If it isn't verified, then you have a discrepancy, and you work that out. Maybe you were wrong, maybe they were wrong, maybe somebody else gets something that confirms you or them. And you work on it until everybody agrees that this is what really happens. Okay. When you report, it has to be readable, comprehensible, and repeatable by anybody who might want to repeat the experiment, whether here or in some other lab. Okay, very good.